Hello, my name is Caitlin Chapman and this is my Lab 4 bar magnets video report. And the purpose of this experiment was to see how changing the distance between a small bar magnet and a magnetic field sensor would affect its response. And we used the Biot-Savart law and the magnetic field of a dipole equations. And the main result of our experiment was that increasing the distance will decrease the magnitude of the magnetic field. So for our experiment, our system was the phone magnetometer, and the surroundings were the bar magnet and the earth. And the initial conditions for the experiment is that the phone would be oriented so that the x component of the magnetometer was equal to 0. And for the on-axis field details of the portion of the experiment, we moved the phone along the axis until the x value would read different values that were desired for our experiment, like 20, 70, 120, 170, and 220. And then we'd record how far away the phone was from the magnet. And we did that three times for each value, and then we took the average. Now for the second part of the experiment, we worked with the off-axis field, and we measured the direct distance for whenever the magnetic field read 100. We would record the y component of the Earth's magnetic field, and then we would move the phone the measured distance from before directly in the y direction. And then we would record the components of the magnetic field and adjust the y component for the Earth's magnetic field. And once again, we would repeat this 3 times. This is a chart of all of our recorded data from both parts of the experiment. On the left side above, we have all of our values for the on-axis field. And then on the bottom, we have all of our values for the off-axis field that were recorded. And over here, we can see a chart that was generated from all of these recorded values that is represented by a linear regression right here. It says the natural log of the x component of the field is equal to the natural log of k plus n times the natural log of r. And we have this chart back over here on the right side. And so that linear regression gives us the slope, which is going to be n, and the y-intercept, which is the natural log of k. And then we used that and plugged it into the kr to n equation to solve for our dipole moment. And we subtracted the value we measured from Earth's magnetic field from the off-axis y component to get the corrected magnetic field for the y direction. And what we notice is that as the magnet gets closer to the magnetometer sensor, the x component of the magnetic field exponentially increases. And so this was the glow script code that was generated to kind of model everything that we were seeing here. And it starts up here in the right corner. And so this is where we created our function. And this is where we created all of our arrows and scaled everything to represent the field lines. And yeah, and this is us creating the 45-degree one. And this is what it looked like when we were all done. And so the general relation that we saw in the model and in real life is that the distance between the magnet and the magnetometer and the effects of the magnetic field are inversely related. And some sources of error that we may have had were that there were many electronics around the table which could have interfered with our magnetic field, but we did our best to keep them at a far enough distance, but sometimes it just doesn't work. Also, we used our cell phones, which aren't always 100% accurate, and we had a lot of inconsistent measurements that were throwing off our data. And so if we hadn't oriented our experiment to compensate for magnetic north and instead laid out our meter stick at an intermediate angle with respect to Earth's magnetic field, our results would have changed a little bit. The x and y components would definitely be different, but the z component not so much. And if we were to stick 2 identical magnets together end to end and run the experiment again, the observed field would roughly double, and the distances would likely increase due to the stronger field. Thank you.